In this video, we'll take a look at transitions between vibrational energy levels as mediated by electromagnetic radiation. That is, we'll be looking at vibrational spectroscopy. Now, when we talk about transitions mediated by electromagnetic radiation, of course, has two components to it, electric field component and a magnetic field component. It turns out for most types of spectroscopies that are used by chemists, the most important is the electric field component. There are exceptions. For example, nuclear magnetic resonance spectroscopy involves an interaction dominated by the magnetic field component, but the ones we're going to be talking about right now are those dominated by the electric field component. Of course, we have light behaving as a wave, oscillating through space. If we look at a simple oscillation involving the electric field, what we'll note is that oscillation in the electric field will cause an oscillation in the molecular charge density. So if you think about the electric field as going up and down, up and down, up and down, then the molecular charge density will also oscillate as it goes up and down, up and down, up and down. And under the proper circumstances, this oscillation can induce a transition between energy levels. Now, the magnitude of that transition, the intensity of that transition, is determined by something called the transition dipole moment, which is given by this integral here. And in this integral, the wave function with subscript n, psi sub n, would represent the initial energy level, and the wave function represented by m would represent the final energy level. So we're talking about a transition between level n and level m with the corresponding wave functions psi sub n and psi sub m. The operator here in the middle is called the electric dipole operator, and we won't be concerned right now with the form of that, but it is again based on this interaction of the oscillating electric field with the charge density of the molecule. Now, if it turns out, if you do a calculation and you find that this transition dipole moment is equal to 0, that means the transition is what we call forbidden, and it will not occur. So this leads to something called selection rules associated with transitions for different types of spectroscopies. And again, we're talking about vibrations here, so we're going to take a look at the transitions between vibrational levels. So for example, consider a transition between n equals 0 and n equal 1, where we're starting at n equals 0. You'll remember from our previous video that most molecules were in the lowest energy state, n equals 0, at room temperature. So when we do infrared spectroscopy, most of the time we're looking at transitions where the molecule is in the n equals 0 state and absorbing energy to go to the n equal 1 state. As you'll recall, then the energy difference between these two levels is equal to h nu, where nu is the frequency of the vibration. We talked about this in an earlier video. And in order to induce a transition, of course, the photon must have the same energy as this energy difference. We know that the photon energy is also given by h nu, where nu is a photon. Now, this of course means that according to the harmonic oscillator approximation, the frequency of the vibration is equal to the frequency of the photon, and this happens to correspond to the infrared region of the electromagnetic spectrum. So again, when you're doing an infrared spectrum, you are probing vibrational transitions within the molecule. Alright, so the selection rules which determine whether a transition will occur and what kinds of transitions can occur are governed by the transition dipole moment. And we first have a gross selection rule, which very simply says that the dipole moment must change during the vibration. So we'll take a look at specifics in a minute, but if you think about a diatomic molecule, as the atoms vibrate back and forth, remember we can more or less consider the bonds to be springs in these vibrations, so we're getting a stretching and a contraction, a stretching and a contraction as they vibrate. If we're going to be able to induce a transition that we'll observe in the infrared spectrum, the dipole moment has to change during that vibration. If it doesn't change, then we won't induce a transition with the electromagnetic oscillations. The other selection rule is that the quantum number may change by only 1 unit in these. So it can go from 0 to 1, it can go from 1 to 2, it can go from 2 to 3, but we can't have harmonic transitions. Harmonic transitions refer to those where we're changing by 2 or more units. Those are forbidden according to the harmonic oscillator. So for example, we consider these energy levels here. The n equal 0 to 1 transition would be allowed, and the 1 to 2 transition would be allowed, but the 0 to 2 transition, which is a harmonic transition, would not be allowed. Alright, so let's start taking a look at some specific molecules. First, homonuclear diatomics. We know that homonuclear diatomics like H2, N2, O2, etc. Have no dipole moment. But that doesn't mean that infrared absorption can't occur because the rule is that the dipole moment must change. So does it change during the vibration? Well, in the case of homonuclear diatomics, no, it does not. Again, if you consider a stretching vibration between two atoms, like the hydrogen atoms here, they pull apart and they come back together, they pull apart, come back together. The charge separation is changing in the molecule as it goes through the vibration, but the dipole moment is still 0 throughout that vibration. You'll remember dipole moment is defined as charge, the charge that's separated multiplied by the distance separating the charge. And even though the atoms are shifting, the overall process is one where the dipole moment is still 0 in this case. Remember, it's like think of it like a tug of war. Since the atoms are the same, it's always going to be equal to 0 during a stretching vibration. And so what that means is that homonuclear diatomics won't exhibit an infrared spectrum. The transitions are forbidden. They are IR inactive. And so when you do an infrared spectrum, you don't have to worry about N2 or O2, which of course are in the atmosphere, interfering with your spectrum. You'll recall when you've done infrared spectra, at no point have you evacuated the chamber, removed the air. If N2 and O2 were infrared absorbers, you would have to use a vacuum to pump out the air in the chamber in order to get a clean infrared spectrum. So we don't have to worry about that because those transitions are forbidden, because in those homonuclear diatomics the dipole moment doesn't change during the vibration. Alright, let's look at a heteronuclear diatomic. These are infrared active, and specifically let's take a look at a molecule like hydrogen chloride, which has a dipole moment, partial positive charge on the hydrogen and the partial negative charge on the chlorine, and it goes through a stretching process, and as it stretches the charge separation changes. So the dipole moment will change during this vibration. So it is infrared active. So we also have the rule that the transitions are just 1 unit. So we can expect in the infrared spectrum to see a 0 to 1 transition dominating. If we heat it up, we might also see the 1 to 2 transition. Now, according to the harmonic oscillator approximation, the transition energy for 0 to 1 and 1 to 2 would be the same, so they would occur at the same frequency in the infrared spectrum. You wouldn't get a different frequency corresponding to each. We'll find that this is an approximation, and that we will see that these energy levels differences are not the same as we climb the vibrational energy level ladder, and that will affect the infrared spectra that we observe. This is something we'll talk about in a later video. But according to the harmonic oscillator approximation, the differences are going to be the same. Alright, polyatomic molecules. Now these are molecules with 3 or more atoms, and they will have more than one vibrational mode. In homonuclear diatomics and heteronuclear diatomics, we see that the only type of vibration is a stretching vibration. But in polyatomics, we can have other types of vibrations. Now, the number of vibrations that we have depends on the number of atoms. In a nonlinear molecule, we have 3n minus 6, n being the number of atoms present. So if a molecule is water, for example, we'll have 3, which has 3 atoms, we'll have 3 times 3 minus 6 for a total of 3 vibrations, 3 different types of vibrations that occur in water. And they occur at different frequencies. So we'll take a look at those in a little bit. For a linear molecule, the rule is there are 3n minus 5. So consider carbon dioxide, which is linear, with 3 atoms. So it has 4 vibrations, different types of vibrations. Now, whether these vibrations occur or are observed in an infrared spectrum depends on whether the dipole moment changes. So as we go through a few examples, we'll find vibrations where the dipole moment does change, and that means they will be occurring in the infrared spectrum. But we'll also find there are certain types of vibrations where the dipole moment does not change, which means we won't observe those in the infrared spectrum. Alright, so let's take a look at water. Now you remember there were 3 vibrational modes in water. Here are 2 of them. The symmetric stretch, and we refer to this as a symmetric stretch because you can see all the atoms they're all moving away from each other, kind of in a synchronous fashion in this situation. So both oxygen-hydrogen bonds are stretching at the same time. The frequency or the wave number that would appear in the infrared spectrum is at 3657 wave numbers. Now you can probably see that in this circumstance, because water has a dipole moment to begin with, that has of course, a partial negative charge toward the oxygen and a partial positive charge between the hydrogens. As the stretching occurs, that dipole moment is going to change, so the symmetric stretch will appear in the infrared spectrum. Then we also have what's called an antisymmetric stretch, and you can see in this case where one OH bond is stretching, the other OH bond at the same time is contracting. That's why it's called an antisymmetric stretch. This too will result in a change in the dipole moment, so this too will appear in the infrared spectrum. The third vibration in water is a bending mode, which I've drawn here, and you can consider this kind of like the molecule flapping its wings. The hydrogens are going up and down in this bend that occurs. And so, in this case, again, as you can probably imagine, the dipole moment changes during the bend. So this is infrared active. So in water, we'll note that all 3 of the vibrational modes are infrared active. All 3 occur with a change in dipole moment. All 3 will appear in the infrared spectrum. I have some videos of these motions that I'll be uploading for you to take a look at, so you'll actually be able to see the animations, the motion of the atoms in these animations. Alright, carbon dioxide, which you recall is a linear molecule, has 4 vibrational modes. There's a symmetric stretch, which is indicated here, occurs at 1388 wave numbers. And we can think of that as a situation where the carbon-oxygen bonds are stretching simultaneously, moving out, then moving in, then moving out, then moving in. Carbon dioxide, of course, has 0 dipole moment. So when we look at that, stretching and compressing, at no point will that dipole moment change. We'll come back to that in a few seconds. There's also an antisymmetric stretch where one bond will stretch and the other bond will compress, and vice versa, and that occurs in carbon dioxide. Molecule remains linear throughout that process, but again, one oxygen moves toward the carbon while the other oxygen moves away, and that has an impact on the dipole moment, as we'll look at in a few seconds. And then finally we have the bending vibration. Now remember, CO2 has 4 vibrations total, but 2 of those are the bend vibration. And so we have this depicted here. Again, you can think of it like it's flapping the wings. The oxygens are moving up and down. in these vibrations. And so here's one where the vibration is in the plane of the slide here, but also it can be out of plane, so we can have the oxygen atoms coming out toward you in this diagram and going back behind it in this diagram. So there are two different modes, one where it's kind of going up and down, and the other where it's going in and out. These modes are at the same frequency, and that means they're degenerate. They're doubly degenerate. This is a doubly degenerate vibrational mode. All right. Now, again, going back to the IR activity, as indicated earlier, the molecule has zero permanent dipole, and in the case of the symmetric stretch, at no point does that dipole moment change from zero throughout the vibration. So because of that, the symmetric stretch is infrared inactive. It does not appear in the infrared spectrum. On the other hand, if we look at the antisymmetric stretch, we're going to see that the dipole moment will change because one oxygen moves toward the carbon and the other moves away. So there will be a non-zero dipole moment at points through that particular vibration. So because the dipole moment does change from zero during the vibration, the antisymmetric stretch will appear in the infrared spectrum. And then if we consider the bending mode, going up and down or in and out, as you can imagine, the dipole moment also changes, because you can certainly see in the bend here in this particular snapshot where the oxygens are now below the carbon, clearly that molecule would have a dipole moment. So once again we can see that it changes from zero, the dipole moment changes, so the bending mode is also infrared active. So the vibrations of carbon dioxide, the symmetric stretch will not appear in the IR spectrum, but the antisymmetric stretch and the bending modes will appear in the IR spectrum. And so here is an example of the infrared spectrum of carbon dioxide. You can actually, if you were to actually go to the infrared spectrometer and kind of blow into it, it would pick up the carbon dioxide in your breath. And you can see here this central peak. There are lots of little peaks in the spectrum, and we'll talk about some of these in a later video when we look at take a more complex view of infrared spectroscopy. But the central peak is the one here that represents the bending mode, carbon dioxide. I'll add that when we talk about global warming and the carbon dioxide in the atmosphere and the role it plays, it's the bending mode that's the most important mode because the frequency at which it absorbs, which is right around here at 667, 668 wave numbers, actually is a frequency that matches the infrared output from the Earth's surface very well. So it absorbs a great deal of the radiation emitted by the Earth's surface. Now here is the infrared spectrum of the carbon dioxide antisymmetric stretch. You'll notice two peaks here, and again we'll talk about that, the reason for that, in a future video. But again, we're just showing the infrared spectrum of CO2. So this ends our preliminary discussion of infrared spectroscopy according to the harmonic oscillator approximation. In future videos, we'll be taking a look at a more complex analysis of the infrared spectrum and actually deviations from the harmonic oscillator approximation and how we must account for that, as well as look at the role that rotations play in the spectra that we observe in the infrared. Stay tuned.